All right, welcome to lecture 5. In lecture 5, we're going to be talking about t-tests and ANOVA. T-tests will compare two different groups. We'll talk about a one-sample t-test, paired samples t-test, and a two-sample t-test. And then finally, we'll finish this lecture talking about ANOVA, which is when we want to compare more than two independent groups. All right, this I want to just continue to drill because this is the process that we go to for significance testing. And the only thing that really changes here is the test statistic that we're calculating and then how we find that p-value. So the distributions we use look a little different. So the tables that we go to find those p-values may be a little different, but the process is the same. So we state our null and alternative hypothesis. Generally, that null hypothesis says no difference, there's no relationship. So for today, since we're talking about differences between groups, that null will be that there is no difference between groups. All right. Then we go ahead and calculate the test statistic. So we'll have four different formula that we use today: the one sample t-test, dependent or paired samples t-test, independent samples t-test, and then the ANOVA. We'll find a p-value and its critical value. We'll make that determination. What is our critical value? Generally 0.05. And then we'll state a conclusion, whether or not our statistic would be observed due to chance alone based on the probability. What do we conclude? So as I just mentioned in the previous slide, we're going to use this four-step process to learn 4 new statistical tests. Okay, so in the last lecture, as we went through this process that I just outlined, we learned about using the one sample Z statistic. So if you were to go back to that formula, you'd remember that it is Z equals X bar, the sample mean, minus mu, which is the population mean, over sigma over the square root of n. Okay? And so what we do here is we realize that often we may not know the population's standard deviation or the sigma. So in that case, what we do is we use the sample standard deviation, or S, to substitute that in. And so you can see that in this formula right here, we've just taken and replaced that population standard deviation with the standard deviation of the sample. So this is the one sample t statistic. Okay, so we have a family of distributions. We'll label them all the t distributions. That they're not normal distributions, but they're very similar in shape. They're symmetric about 0, and they're bell-shaped. So if you see the graphic down below, kind of study that, because what that's telling you is each one of these t distributions is associated with some degrees of freedom. In the case of the one sample t-test, we calculate the degrees of freedom by using the sample size minus 1. All right? And what you'll notice is as the degrees of freedom go up, or as our sample size gets larger, the density curve of the t distributions gets closer and closer to being normal. Okay, so as I have a larger sample, my curve, my t distribution, will approximate a normal distribution. All right, so we're going to go ahead and practice. So on this slide, I just have the problem itself, and on the next slide, I'll work out the problem so we can do it together so you can check your answer. But take time now to do this, go through these 4 steps, and then I'll go through it in the next problem. So the question is, what if my research question is, does one region's caseworkers differ from the states with respect to the number of cases processed per month? So in the region, I have an X bar, or a sample mean of 24.74 cases. The sample size is 30, and the standard deviation of that sample is 4.16 cases. right? In the state, I know that the state mean is 23.12 cases. So the question is that difference of about 1.5 cases, is that statistically significant? Is there something systematic going on about this region? Or could we assume that this difference is due to chance alone? So state your null and alternative hypothesis. Use the formula on the previous slide to calculate, or I guess it's 2 slides ago, to calculate the t-statistic. Remember, it's the same formula as the one sample z statistic, but we're substituting in the sample standard deviation. Then calculate the degrees of freedom, all right? And remember what that is under the one sample t statistic. And you can go into your book, and it kind of depends on if you have what edition you have, but it's table C or D. The idea is to look at the t distribution of critical values. There'll be a table there. And then I want you to assume a two-tailed hypothesis test with a significance level of 0.05. That's the critical value that I've set. And then come to a conclusion. Do we accept or reject the null? Or do we fail to reject or reject the null? Another way of saying that. All right, so I'm going to work through this problem. I've erased the steps here, but we should almost have them memorized by now. But remember, number 1 is to state our null and alternative hypothesis. So the null hypothesis is that this sample mean will equal the mean for the state. Okay? Or another way to write that is that the sample mean is going to equal 23.12. All right? And the alternative would be that this sample mean will not equal 23.12. Okay? Or will not equal the mean for the mu for the state, or the mean. All right, so number 2, now I calculate my test statistic. So for the one sample t, it's going to be that x bar minus mu over the sample standard deviation and the square root of the sample size. So we would do 24.74 minus 23.12 over 4.16 divided by the square root of our sample size, or 30. Okay? So if you were to work out all that calculation, I get 2.13. That is my test statistic. Now we're going to remember, in number 3, look up the p-value. And this is the table over here that I've copied from your book, or it should look something like this on that table. And I said to assume confidence level of 0.05 for a two-tailed test. So we're going to be right here, 0.05 for a two-tailed test. And the degrees of freedom I need to calculate. And if you remember, that's the sample size minus 1. So it's 30 minus 1, which is 29. So that will put me right here, 29. So now I know I'm at a 95% confidence for a two-tailed test. Degrees of freedom are 29, and then I just go over and I find my critical value here of 2.045. 2.045. Okay? So now, knowing my critical value, I compare these two. So 2.045 is less than the t-statistic I calculated, 2.13. So if I have my t-distribution, remember it looks kind of like a normal distribution, and here's my mean of 0. If my critical value is 2.045, my value that I calculated, 2.13, is more extreme than that. So I'm going to reject the null. Okay? Hopefully you got that. All right. Okay, so let's practice one more time. In this case, the only information I've changed was the sample size. So the sample size went from 30 in the previous problem to 15. So go ahead and go through the same process. We know that step 1's the same. The null and alternative will be the same. Nothing's changed there. But we need to recalculate our t-statistic. So go ahead and do that. And then also step 3 is a little different because our sample size has changed. So those degrees of freedom changed. So recalculate that, find your critical value, and then tell me if we accept or reject our null. All right. So pause the video, go ahead and do that, and then I'm just going to work it on this slide, just kind of give you the answers. Okay. So to recalculate our test statistic, I went ahead and substituted that 30. So it's going to be 24 point, oh, that does not look like a 4. That's a 4. 0.74 minus 23.12 over, in this case, 4.16 is the same, but then we have the square root of 15. And if you recalculate that, I get 1.51 is my t value, okay? And then if I go to a t-distribution chart and I look at the degrees of freedom and need to calculate them, well, I know degrees of freedom is my sample size minus 1. So in this case, it's 15 minus 1, which is 14. And when I look on that table with a two-tailed test and a p-value of 0.05, my degree of confidence, I get a critical value of 2.145. Now in this case, 2.145 is greater than my test statistic of 1.51 that I calculated above. So if it's greater, that means that in the distribution, my 1.51 lies closer to the mean than the critical value I set of 2.145. There's my 1.51. In which case, what do I have to do? Well, I have to accept the null, or I failed to reject the null hypothesis. So in this case, what do we learn? Well, none of the information changed except our sample size got smaller. So as the sample size gets smaller, notice our critical value is going to increase. There's going to be more uncertainty, okay? And the t-distribution, it's going to flatten out and kind of have fatter tails as we get a bigger sample size. Because remember, as we get a smaller sample size, because remember, as we get a bigger sample size, the t-distribution is going to approximate that normal distribution with a mean of 0 and a standard deviation of 1. All right, now we're moving on from just looking at one sample. So we had the one sample Z statistic and the one sample T. Now we're going to look at two samples, okay? And the first one we'll start with is the matched pairs t-test. But if you Google it, it may also be called the pairs t-test or related t-test or dependent samples t-test. There's all similar names, but the idea is that there's some way in which the samples that were selected were not selected independent of each other. So I think in the first class, we talked about this idea of pre-post testing, before, after, right? Where each individual person's identified or at least sampled at two different time points, okay? So we might not have one way in which that's dependent. Another might be that we match individuals based on certain characteristics that they have, their age, their years experience in the job, how much education they have. In that sense, we're selecting our samples based on some known characteristic, in which case they wouldn't be independent, right? Because they're matched on those characteristics. And a final could be thinking about couples, couples that are selected and then paired together. And in this case, the unit of analysis wouldn't be an individual, but it would in fact be this couple that we're looking at, how they respond, maybe before and after some event. Okay, so for the matched samples, or the matched pairs t-test, or matched samples, or dependent samples, lots of names. The idea is that we are going to be using the mean difference between the matched pairs, okay? So we calculate that mean difference, which we call d bar, so that mean difference, It's we add up all the differences and divide by the total pairs that we have, okay? So this is an example from your book. There's often the theory about the full moon and how hospitals and even schools, they can, misbehave, or at least behavior incidents seem to arise. So here we have aggressive behavior for patients with dementia. And the sample size here is we have 15 different cases. And they measured their aggressive behavior on days when the moon was full and then on other days, okay? And then they took that difference. So those are the columns. You have patient, moon days, other days, and then difference. That difference is the D that we're looking for. So in order for us to get the mean difference down here, all we're going to do is we're going to sum all the differences. So we add up this column. Oh, that was terrible. And this column. Add those up and you get 36.49. And then we divide by the total number of, in this case, matched pairs. So there, N here is 15. So you can see how the formula works, and we get 2.43. That's the average difference across these 15 patients. Okay, now we also need to know the standard deviation of the difference, and we can calculate that once we've calculated D bar, or the mean difference for all of our matched pairs. So this is the equation we use. Hopefully we're getting a little more comfortable with this, but it is the sum of each deviation or each difference, so each individual D, lowercase d, so for each of these matched pairs, that difference minus D bar squared, and we add all those differences up, and we divide by the sample size minus 1. So in this case, 15 minus 1. And then just like we did with standard deviation, to get it back on the scale, we square root it. So since we squared things, we're going to now take the square root of that. Okay? So what you would need to do is, going back to the table previously, you would need to do that calculation for each one. So you'd need to take each pair sample, you would find the difference between that and D bar, you would square that difference, you would do that for each one, you'd add them all up and divide by n minus 1, and then take the square root. So we did an example of that in Excel, the standard deviation, in one of our previous lectures. But here I just did that for you, and the calculation is 1.46. Okay, now we have a formula for the matched pairs t-test. Now this looks very similar to the one sample t-test we just did, except we've substituted x bar for d bar and the standard deviation of the sample for the standard deviation of the difference. So here, notice we've got t equals d bar, that's what we calculated, the mean difference minus mu. All right, and mu is usually 0, right? That we would expect that there would be no difference. So for these dementia patients, we would expect that there would be no difference between times when the moon was full and times when it wasn't, if there wasn't something going on with the full moon, right? If the null hypothesis were true. So d bar minus mu over the standard deviation of the difference, which we just calculated on the previous slide. I told you that was 1.46, over the square root of the number of matched pairs. So that's 15. We have 15 patients that we looked at 2 time points, okay? So here is the formula calculated. 2.43, we found that was d bar. We subtract 0, which is the expectation that there's no difference. The standard deviation of the difference was 1.46, and I gave you that, over the square root of the sample size, or 15 matched pairs. And then you get a t value of 6.45. Okay, so remember our process. We stated a null and alternative hypothesis, or at least that's the process we should have gone through. So the idea being that there's no difference for the null between times when these dementia patients have a full moon outside and times when they don't. And the alternative would be that there is some difference, right? So we're going to do a two-tailed test. We calculated our t statistic, which I think, if I remember right, 6.45. And we know that we need to go to our t-table and have the degrees of freedom. So that is 15 minus 1 or 4. Oh no, this is fading. Sorry, don't fade. All right. So looking at your table, if we have a two-tailed test, assuming a two-tailed test with a significance level of 0.05 and a degrees of freedom of 14, well, that's the same as the problem we did previously, but the t to critical value would be 2.145, okay? That would be here that I got from the table. And ours was 6.45. I hope that's right. And so we know that the value we calculated was greater than the critical value. So if I were to draw it, we have some t distribution. Here's the critical value at 2.145. Well, mine's out here at 6. So we would definitely say that we could reject the null hypothesis and say there's something odd that goes on with dementia patients when the moon is full. Okay, now we're shifting gears from dependent samples t-test to independent samples t-test. So this is where each of the subpopulations are entirely independent of each other. So we would calculate the mean for each of these samples, and each of these population means, they'll be independent of each other. We would calculate them separately, okay? So thinking about what are these independent samples, we talked about, well, this could be in a school, boys and girls in an elementary school. Or it could be the differences between those who are English learners and those who aren't. Or it could be some set of patients that you have in your hospital that have a certain disease versus those who don't. Or it could be individuals of color versus white, right? So you can pick it, but the idea is you have two independent samples, that there isn't any overlap between the two, and that they are limited to just two different independent groups, that there aren't more than two. So I think now is a good time to pause and remind ourselves that we're still talking about a sampling distribution. So for all of these tests, we're thinking about a sampling distribution and where our sample lies within that, okay? So we can make inferences about the population. Well, in this case, with an independent samples t-test, we're thinking about a sampling distribution of the difference of means. Okay, so let's say I'm interested in looking at the differences between PhD students and master students, and let's assume that there's no master student that's also a PhD student. So these are two independent groups, and I want to ask them about their graduate experiences here at NC State, and I want to test whether or not there are any differences about their attitudes. Okay, so I go in and I grab a sample. I can't get every one of them, but I go down to the 4th floor and I find some and I ask them my questions, right? I give them a survey, let's say. And then I go back and I collect my data. Well, obviously the difference between those two groups from the sample that I have will just be one of an infinite number that I might sample from this population, especially if we think about all masters and PhD students, okay? So we could, with repeated sampling, go in and create a sampling distribution of these differences, okay? And with respect to the sampling distribution versus sample mean, we learned that the population mean mu was equal to the mean for the sampling distribution. So what does it mean for if we have a sampling distribution of the difference of means? Well, that's going to depend on our null hypothesis. So the null hypothesis in the case of the independent samples t-test in general is going to be that there is no difference between the means of these two populations. So to go back to our example, there's no difference in attitudes or perceptions about graduate school from master's and PhD students. That is, mu sub 1 equals mu sub 2, or mu sub 1 minus mu sub 2 equals 0, okay? Two ways to state it. So the idea is if we expect the null hypothesis is true, that we'd expect the mean for the sampling distribution of differences of means to be 0 as well, okay? And we'd also expect that any observed differences between these two sample means would be small and close to 0. So once again, the units that we're measuring on will vary. So some might be test scores, some might be student poverty, some might be some survey measure that we gave. But we're going to standardize this difference and put it in a standardized distribution to see how far it varies or is different, departs from this mean of 0, okay? So that's what we're going to be testing against. All right, so here is the formula or the test statistic, the t-test statistic for independent samples, okay? I know it looks confusing. It's definitely more confusing than other formulas we've looked at, but the general thinking behind it is very similar to the other t-tests and the one sample z-test that we've already looked at. So remember, in the numerator, we looked at the difference between either the sample and the population. Well, in this case, we're going to look at the difference between two samples. So x bar 1 minus x bar 2. So sample 1's mean minus sample 2's mean. Okay, and we're going to subtract the difference that occurs in the population. Now, we just talked about our assumption is going to be that the null hypothesis is 0, that there's no difference in the population. Okay, so this mu sub 1 and mu sub 2, if you look down here, we're going to assume that that equals 0. Okay, that there is no difference. But then we're going to divide the denominator, if you remember, has always had something around standard deviation and sample size, right? So it's similar here. We're going to call this the standard error of the estimate, and it's defined by the sample standard deviation squared, and we called that the, if you remember, the variance. Okay, it's the variance or the standard deviation squared from sample 1 over its sample size, so n sub 1, plus the variance of the second sample, or the standard deviation of sample 2 squared, over its sample size. Okay, you add those up and you take the square root of that. That's what's going to go under here. So assuming that we are testing a null hypothesis that there is no difference in the population, this is your one sample t statistic. And the only other assumption we make is that there are unequal variances in the population. Okay, so it's a safe kind of conservative estimate to make that in the population, these two samples may have different variances. All right, now I'm adding this slide in here because there is another formula you need to be aware of for the independent samples t statistic, and that is when we are assuming that the population variances are equal. If we do that, then the standard error of the estimate needs to change, and this is how it changed. So you still have the variance of sample 1 and the variance of sample 2, and then you're going to use these sample sizes in a different way, okay? Now, Stata is always going to use this formula when it does its calculation, but if we specify the option Welch, then it will do the unequal variance assumption, okay? For our point of view, we can use either, right? We can just let Stata run, but I just want you to be aware that there are these two formulas in case you're Googling it and you feel like you got a different formula than the one that's in your book. Okay, so just to orient you to where we're at, we stated our null and alternative hypothesis. The null hypothesis was there was no difference in the population between these two means, or we said mu sub 1 is equal to mu sub 2. The alternative would be that they're not equal in the population, okay? Then we showed you just on the last two slides the formula to calculate the t statistic and how to do that. So now having got our t statistic, we go to step 3, which is to find our p-value, right? So that we know if our value is more extreme than the critical value that we've set. Now, the t-distribution, the t-statistic does not have a t-distribution since we're replacing two population variances with two standard deviations, okay? But Stata is going to go ahead and approximate that for us. If we don't have Stata doing it for us and we have to do it by hand, One way to approximate the degrees of freedom is to use the smaller of the two sample sizes if they're unequal sample sizes, okay? If they're the same sample size, then you just pick one, all right? That's assuming unequal population variances, all right? But the whole point of this is we need to know our degrees of freedom so we can go to the t-table and figure out that critical value, okay? Having set our p-value and whether or not we're a one or two-tailed test. In this case, it'd be a two-tailed test because there's either some difference or not a difference. But we want to go into that so that we can make a judgment for step 4. Okay, if we are assuming equal population variances, then the degrees of freedom are going to be the two sample size. You're going to add up the two sample sizes and you're going to subtract 2. And that's going to be the degrees of freedom that you use, okay? So it just depends on whether or not it's equal or unequal. Stata is going to go ahead and do a lot of this behind the scenes. But for the next problem that we're going to do together to practice on the next slide, we're going to assume unequal population variances. Okay, here is a practice problem that we're going to practice with an independent samples t-test, okay? So we have our 4 steps here, and the problem is that students in Mr. Jones' class were randomly decided to receive a new program, Miracle Read. This promises to teach anyone anywhere to read. So here are the results from the end of year exam. Miracle Read students scored an average of 53.92. There were 11 of them, and the standard deviation was 5.15. The other students in the class scored lower at 50. There were 17 of them, and the standard deviation was 6.46. So the question is this 3 to 4 point difference, almost 4 point difference, was that due to Miracle Read, or is this just due to random chance? Okay, so go ahead and work through each one of these 4 steps, and then on the next slide, I'll do it with you. All right, so here we go, going through this problem for each step. So we know that the null hypothesis is going to be no difference. So we would write that mu sub miracle, I'll just put mu sub mer, is equal to mu sub reg, or the regular students that did not receive the treatment, okay? Or that mu sub mer minus mu sub reg equals 0. Okay, we could write it either way. An alternative hypothesis would be that mu sub mer is not equal to mu sub reg, or that there is some difference. It might be positive, it might be negative, but it's non-directional. So that would put us at a two-tailed test. Okay, so we stated our known alternative. Now we need to calculate the test statistic. I asked you to do it with unequal variances. So the formula we're going to use is T equals X bar 1 minus X bar 2. Okay, remember that we really would have mu sub 1 minus mu sub 2 here, but if we take these in here, we know that that's going to be 0. But we're going to put this over the standard deviation, or the variance, or the S1 squared over N sub 1 plus S, that's a 3, sorry, that's an S, S2 squared over N sub 2, that's a plus sign, and we're going to take the square root of that, okay? So if you go in and you plug in each one of these numbers to where they need to go, so 53.92 minus 50 over, here's N sub 1, S sub 1, 5.15 squared would be S sub 1 squared, S sub 2 squared would be 6.46 squared. Okay, we're plugging in those numbers, and then you have N sub 1 and N sub 2. And if you do all that calculation, I get 1.77 as my t-value. Okay, So now for step 3, we need to calculate our degrees of freedom. And when we're saying with unequal variances, I said, well, Stata would do this for us, but we can approximate it by taking the smaller of the two sample sizes and subtracting 1. So in this case, n sub 1 equals 11 and n sub 2 equals 17. So let's go ahead and take the smaller of these, n sub 1, subtract 1, and we'll say our degrees of freedom are 10. Okay? So now we have our degrees of freedom 10 in our chart. We know it's a two-sided test, and we'll do the same 0.05. Okay? And so if we go up here, we get a critical value of 2.228. Okay? So 2.228. Well, 2.228, if we now, to make our determination in step 4, we compare these two. And 2.228, our critical value, is greater than the t-statistic we calculated at 1.77. So that means that if we were to look at the distribution here, our critical value, 2.228, is outside the value we calculated at 1.77, okay? So if we fall inside that value, then we know that we fail to reject or we need to accept the null hypothesis, okay? So is miracle read really a miracle? Well, according to this study, no. We can't say with the degree of certainty that we'd like to have that these students are systematically different or better, even though their average score is about 4 points higher. Phew, all right, you're exhausted. I'm exhausted, but we're gonna keep going. Because ANOVA just builds right off of this and saying that, well, what if I have more than 2 group means? Okay, I'd like to compare 3 or 4 or 5 group means. In that case, we're gonna turn to an analysis of variance. In essence, we're examining whether or not the group means difference from one another according to with respect to a particular score or variable, okay? And the statistic we're gonna be calculating is called an F statistic. So we've had Z statistics, we've had T statistics, now we're on to an F statistic with respect to ANOVA. Okay, so what are some examples? Well, maybe we want to compare student performance by race, ethnicity. So I want to know in a school or a district or a state or across the nation or between countries, whether or not students of different race ethnicities have different performance on some standardized exam. Or maybe I want to look at the difference in comparing enrollment between school level, elementary, middle, high, and other. Maybe attendance patterns by neighborhood or admission rates by municipality. There's lots of different options, but the idea is that you have more than 2 independent groups that you'd like to compare the means to. And again, like all of these tests, we'll get a sample, but it's really the population that we're interested in making inferences about. Okay, so the steps are the same that we've been going through. We're going to go through the same process. We'll state a null and an alternative hypothesis. In this case, we're going to calculate the test statistic, which will be an F statistic. This will measure how far the data are from the null. We'll find a critical value, and then we'll accept or reject the null based on our test statistic and the critical value. Okay, so I'm going to start with an example and give you a visual of how this test works. So again, get the machinery behind it, and then we'll go ahead and go through the 4 steps with this example. But essentially what we want to know is if student performance is significantly different across differences in students in different grouping levels. Okay, so we have our A grouping level, our B grouping level, and C grouping level. So we'd like to do a t-test, but we have 3 groups, not 2, so we need to turn to an ANOVA. And the idea is to look at what the test is going to do. It's going to say, well, is the variance in test scores between student groupings a lot greater than the variance within student groupings? If so, that's going to provide evidence that there are actual differences between these groups. So I'm going to say that again and try to say it in a different way. If student A, group A, group B, and group C you look at the standard deviation within each one of those groups and it's very small, but then you look at the variance or the difference between these groups and it's large, you would say, wow, these groups are pretty homogeneous, they're pretty similar, but their performance is quite different when I compare across them. And so if the between group difference is a lot larger than the within group difference, it's going to provide some evidence that there are differences between these groups. All right, so I love visuals, so I'm going to provide you a visual of a box and whisker plot. What a box and whisker plot captures is where the median is and where the kind of middle 50% of the data lie, and then the whiskers, that's the box, and then the whiskers provide you the rest of the observations. So I want to try to visualize what's going on with an ANOVA when we're comparing, in this case, we have the example of 3 groups. So I'm going to start with red, and I just want to show you between A and B. Notice here on this left graphic that A, the highest values up here and the lowest values down here. But the overlap between A and B, if you were to take the highest and lowest values, the overlap between A and B is right here. So a lot of the values tend to overlap because we have quite a lot of variation within A. And we have quite a lot of variation within B. And then we have quite a lot of variation here within C. So I'm just going to grab a blue color here and show you in blue, if I take the upper box or upper whisker of C and I take the lower whisker of A, this shows you the students who scored the same range across all 3 groups. And it's pretty large. Now I want you to compare that here with this second graphic. So notice here we have a lot tighter variation within. So A, B, and C are tightly organized around their median, and there's a lot less overlap, particularly when you look at the boxes themselves. So these boxes don't overlap at all. When that's the case, when you have a small within group variation and larger between group variation, that's when your F statistic that we're going to calculate tends to be large. Whereas F tends to be small if the within group difference, this within group variance, tends to be large. All right, so let's go back to our example. Go ahead and take a moment and state the null hypothesis. Okay, so the null hypothesis is that there is no difference between the groups A, B, and C. That is, mu sub A is equal to mu sub B, which is equal to mu sub C. Okay, the alternative hypothesis then would be that mu sub A is not equal to mu sub B, which is not equal to mu sub C. Okay, that there's a difference there between these groups. All right, the F statistic, the formula is that we're going to look at what's called the MS between, or the mean squares between, divided by the mean squares within. Okay? And the rationale, and I've tried to explain it with the box and whisker plots, and I've created another visual here, but the idea is we want the within group variance to be small and the between group variance to be large if we want to find differences between groups. So we're going to compare that red variance, each of the within group, to the overall between group, or the green, the MS between. Okay, like we've been doing, in some sense, we've been calculating deviations from a mean. So in this case, we're going to let Stata do this calculation. So you're not going to have to do this by hand. We'll just let Stata run it for us. But I want you to know kind of the mechanics behind this formula. What it is you're going to need to know what the between sum of squares is. So that's the sum of the square deviations for each of the groups means from the overall mean. Okay? The sum of the squares within is the sum of the square deviations of each observation from that group mean. Okay, so one's each group mean from the overall mean, and the other is each observation from the overall mean. And then the degrees of freedom are a little different. The degrees of freedom between is k minus 1, where k is the number of groups. So that would be 3 in this case, minus 1, or 2. The degrees of freedom within are n minus k, where n is the total sample size that you have in the class. All right, so then the mean squares between and the mean squares within is the sum of each of these, the sum of squares divided by its degrees of freedom. Okay, so that's how you get at the mechanics of this formula, and I think your book goes into some detail. Okay, so now we're on to part 3, right, where we need to find that critical value, and we need to have some confidence level that we're adjusting for, or setting before we go into this. So for the F statistic, remember we have 2 different degrees of freedom. We have the mean squares within degrees of freedom, so one for the numerator and one for the denominator, okay? And so remember how to calculate those. One is the group size minus 1, and the other is the sample size minus the number of groups, all right? As with other tests, we'll compare our F statistic to the critical value, and this is determined by an F distribution. So we've been talking up to this point about Z distributions. We had T distributions that approximated normal distributions, especially as the sample size went up. But in this case, an F distribution is a positive distribution, okay? And we're looking to see where does our F value lie with respect to this critical value that we set. Okay, so we are actually not going to be going through the calculation, even though I kind of have that example up. We're going to do that together in class because we're going to have Stata do some of that calculation. And we can even use Excel if you'd like to kind of go through the process of how each of this works just so you can see it. But really at this point, I want you to understand the intuition behind it. We're comparing that within group difference to the between group difference, okay? And this is an example of how Stata will go ahead and find critical values and give us a cut point and, you know, determine to some, that we predetermined by some critical value. But there are tables. There are tables that will show you, and I just wanted to show here on this slide that you have to know the degrees of freedom for the denominator. So that's n minus k, or the sample size minus the number of groups, and the degrees of freedom for the numerator, and that's just the number of groups minus 1. And so let's say that we're 25 and 2 respectively, and we had a type 1 error rate of 0.05. Remember, that's our willingness to accept some risk that we might reject a true null hypothesis. And the critical value here would be 3.39. So we would compare our test statistic that was calculated to this critical value of 3.39 and determine whether or not there was some difference between groups A, B, and C. And again, we'll be going through that together in class.